Let me ask you something. What's the most alien place you can think of? Mars, the surface of Europa? Some distant exoplanet orbiting a star we can barely see? The answer isn't in space. It's right here on Earth. Right now, beneath the Pacific Ocean, lies a world more hostile than outer space. Complete darkness, near freezing temperatures, pressure so extreme it would crush a submarine like a soda can. For most of human history, scientists believed nothing could survive there. The conditions were simply too extreme. Then in 1960, two men descended to the deepest point on Earth, nearly 11 kilometers down, to a place no human had ever reached. And there, in the beam of their lights, they saw something move. Life at the very edge of what should be possible. Most of what we know comes from rare specimens brought up by probes or caught in fishing nets. But when pulled from their world, the sudden pressure change causes them to expand, rupture, sometimes disintegrate. We see them only as distorted shadows of their true forms. So what's really down there? What lives at the deepest point on Earth? And how do these creatures survive conditions that would destroy almost everything else? If you've ever wondered what exists in places humans can barely reach, make sure you subscribe and turn on notifications, because what I'm about to reveal will change how you see our planet forever. Drop a comment with where you're watching from, and whether you believe life can exist in conditions this extreme. I'm about to take you on a journey to the deepest darkness on Earth. And what we find there will challenge everything you thought you knew about the limits of life. To answer the question of what lives in Earth's deepest darkness, we need to go back to where it all started. Our story begins 150 years ago with a ship called HMS Challenger. In 1872, a British ship set sail on a mission that would change our understanding of the ocean forever. HMS Challenger wasn't a warship. It had been converted into something unprecedented, a floating laboratory. For 4 years, this vessel traveled the world's oceans, stopping at hundreds of locations to measure temperature, currents, depth, and collect sediment samples. The crew used primitive equipment by today's standards. Long ropes weighted with lead, lowered slowly into the darkness until they hit bottom. It was exhausting work, imprecise, but it was a start. Sailing the high seas in those days was dangerous work. Sailors lived by traditions and superstitions. Legends spoke of enormous creatures rising from the depths, gripping entire ships in writhing tentacles and dragging them under. To us, these sound like myths, but for crews staring into thousands of meters of black water, the fear was real. Near the Mariana Islands, they recorded a depth of around 8,200 meters. At the time, it was the deepest measurement ever taken. The crew could barely comprehend it. If you stood at sea level and looked down, that's more than 20 Empire State Buildings stacked end to end, disappearing into blackness. But measuring the ocean's depth accurately was harder than it seemed. It wasn't until 1951 that we got our first truly modern measurement. HMS Challenger 2, named after its famous predecessor, returned to the Mariana Trench equipped with an echo sounder. This device sent sound pulses to the seafloor and measured how long they took to return. The result, approximately 10,863 meters. It was the deepest point ever recorded. And from that moment on, this particular depression in the ocean floor had a name. Challenger Deep. But knowing the depth and actually going there were two very different things. In 1960, two men attempted what seemed impossible. Jacques Piccard, a Swiss engineer, and Don Walsh, a U.S. Navy lieutenant, climbed into a submersible called Trieste. Their goal, to reach the bottom of Challenger Deep. The descent took nearly 5 hours. As they sank deeper, the pressure outside the hull increased relentlessly. 1 atmosphere at the surface, 10 atmospheres at 100 meters, 100 atmospheres at 1,000 meters. By the time they reached 9,000 meters, the pressure was so immense that a plexiglass window cracked with a sound like a gunshot. But they kept going. At 10,116 meters, Trieste touched the sea floor. Piccard and Walsh became the first humans to reach the deepest point on Earth. As the bathyscaphe settled, it stirred up clouds of fine white silt, later identified as diatomaceous ooze, so thick that Walsh described the visibility as like trying to look through a bowl of milk at the bottom. They stayed for 20 minutes, staring into the darkness, and then they saw it. Something moved, a flat, pale shape on the sea floor. It was life. Picard believed he saw a flatfish and other forms of life such as sea cucumbers drifting across the bottom. Later, some of these sightings were disputed since no flatfish have ever been confirmed at depths beyond 27,000 feet. But one thing was certain, something alive was there. Most likely a sea cucumber or other benthic organism. Faint but unmistakable. The discovery was monumental. It proved that even at the very limits of the ocean, where pressure exceeds 1,000 atmospheres and temperatures hover just above freezing, life persists. To understand what lives in the deepest darkness, you need to understand the journey down. The ocean isn't one uniform environment. It's divided into 5 layers, each one getting darker, colder, and more extreme than the last. Picture yourself at the ocean's surface. The water is clear and warm. Sunlight filters down through schools of fish and drifting plankton. This is the ocean most of us know. But beneath this familiar world, the ocean is divided into zones, and the creatures living there have adapted in ways that seem almost alien. The sunlight zone, 0 to 200 meters. This is where life thrives. Microscopic phytoplankton here produce 50% of Earth's oxygen through photosynthesis. They feed zooplankton, which feeds small fish, which feed larger predators like tuna, sharks, and whales. Bright, alive, familiar. But it's only the beginning. The twilight zone, 200 to 1,000 meters. The light fades. This zone holds more fish biomass than anywhere else in the ocean. The bristlemouth, a tiny silverfish, lives here in the quadrillions. It's the most abundant vertebrate on Earth. Bioluminescence appears everywhere. Fish glow to attract prey, confuse predators, or communicate in the darkness. But it's too dim for photosynthesis. Plants can't survive. Everything here hunts, scavenges, or migrates to the surface at night to feed. The deeper we go, the stranger things become. The midnight zone, 1,000 to 4,000 meters. Below 1,000 meters, the last traces of sunlight disappear. The temperature drops to around 4 degrees Celsius. The pressure climbs to 100 atmospheres. This is the bathypelagic zone, the midnight zone, a place of absolute darkness. Here, vision becomes a challenge. Some species, like the owlfish, have evolved enormous eyes to capture what little bioluminescent light exists. Others, like the barrel-eye fish, have transparent heads. Their tubular eyes sit inside their skull, pointing upward, scanning for the silhouettes of prey above. And then there's the anglerfish, perhaps the most iconic deep-sea predator. The female carries a bioluminescent lure, a fleshy appendage dangling in front of her mouth. In the darkness, smaller fish mistake it for prey. They approach, and the anglerfish strikes. The abyss, 4,000 to 6,000 meters. Below 4,000 meters, we enter the abyssopelagic zone, the abyss. Here, life becomes even rarer. The seafloor is a barren plain of fine sediment interrupted occasionally by strange geological formations, underwater mountains, ridges, volcanic seamounts. Food is so scarce that evolution has taken a strange turn. Many organisms here exhibit deep-sea gigantism, growing far larger than their shallow water relatives. Giant isopods, colossal squid, spider crabs with legs spanning 4 meters. The Hadal Zone, 6,000 to 11,000 meters. The deepest realm. Temperature hovers near freezing. Pressure exceeds 1,000 atmospheres. Water becomes dense and viscous, yet life persists. Amphipods grow to 30 centimeters, 10 times their normal size. Xenophores, single-celled organisms, reach the size of soccer balls. They survive on marine snow, a slow rain of organic matter from above. A single whale carcass can sustain an ecosystem for years, and at hydrothermal vents, bacteria convert chemicals into energy through chemosynthesis, supporting tube worms, clams, and shrimp in complete darkness. Only 400 species have been documented across all Hadal zones worldwide, but every expedition discovers more. The deeper we go, the more we realize how little we know. Let me tell you about the creatures that live in this deepest darkness, because what they've evolved to survive is almost beyond comprehension. The organisms found in the deepest regions of the trench are not simply survivors. They are specialists shaped by pressure so extreme that it alters the very structure of biological molecules. Proteins that would normally collapse remain stable. Cell membranes maintain their integrity. Metabolism slows, becoming efficient rather than fast. Evolution here favors endurance over speed. Recent studies have revealed that some deep-sea organisms possess unique genetic adaptations that protect their cellular machinery from pressure-induced damage. These adaptations are not minor variations. They represent entirely different solutions to the problem of being alive. What makes this especially important is not the strangeness of these organisms, but what they demonstrate. Complex life does not require familiar conditions. It requires stability, energy, and time. The trench shows that life can persist at the very margins of what physics allows. Let me introduce you to some of these creatures. The snailfish. At depths exceeding 8,000 meters, the snailfish holds the record for the deepest living fish ever recorded. It's translucent, almost ghostly. Its body is soft, gelatinous, adapted to withstand crushing pressure. It has no swim bladder, the organ most fish use to control buoyancy, because at these depths, a gas-filled organ would be compressed to nothing. The amphipod. These crustaceans, normally a few centimeters long in shallow water, grow to 30 centimeters in the Hadal Zone. They're scavengers, feeding on whatever organic matter drifts down from above. Their bodies are packed with special molecules called piezolites that help their proteins function under extreme pressure. The sea cucumber. These creatures were likely what Picard and Walsh saw during their historic dive. They crawl along the seafloor, processing sediment and extracting whatever nutrients they can find. They're the vacuum cleaners of the deep, essential to the ecosystem despite the harsh conditions. The xenophore. Single-celled organisms that grow to the size of soccer balls. They're among the largest single-celled organisms on Earth. They survive by creating internal structures that help them withstand pressure, and by feeding on bacteria and organic particles in the sediment. And then, there are the creatures we've barely begun to understand. The Hadal snailfish. The Mariana Hadal snailfish, species discovered only in the last decade. Each expedition to the deep brings back new species, new adaptations, new evidence that life finds a way even in the most impossible conditions. Pressure is the single greatest obstacle to exploring the deep ocean. At the surface, we experience 1 atmosphere of pressure. At 10,000 meters, that number climbs to over 1,000 atmospheres. The force is so immense that it can crush a submarine like a soda can, and occasionally it does. In 2014, an unmanned submersible called Nereus was exploring the Kermadec Trench at a depth of 9,990 meters. Without warning, it imploded. The pressure hull failed and the entire vehicle was destroyed in an instant. Pieces of debris were recovered later, scattered across the seafloor. More recently, in 2023, the Titan submersible imploded while descending to the wreck of the Titanic. 5 people were killed. The cause was structural failure. At depth, even the smallest weakness in a pressure hull can be catastrophic. The water doesn't seep in slowly. It collapses inward with the force of an explosion. This is why deep-sea exploration is so difficult and why the technology required to reach the Hadal Zone is among the most advanced engineering on Earth. The first deep-sea submersibles, like Trieste, used thick steel spheres to protect their crew. The sphere was small, cramped, and could only hold 2 people, but it worked. Steel is strong. It can withstand enormous pressure if the walls are thick enough. Modern submersibles like Victor Vescovo's limiting factor have evolved significantly. The pressure hull is made of titanium, lighter, and stronger than steel. The sub is surrounded by syntactic foam, a material that provides buoyancy without collapsing under pressure. Inside, there's life support, 3D cameras, robotic arms for collecting samples, and an array of sensors to measure temperature, salinity, and depth. But even with these advances, deep-sea exploration remains dangerous. Every dive is a calculated risk. Every seal, every joint, every weld must be perfect, because at 11,000 meters, there's no margin for error. So what have we actually learned from these dives? Most deep-sea surveys involve dropping cameras or probes to the seafloor and recording whatever happens to pass by. The field of view is narrow, the time is limited, and the creatures that live there are often too fast, too small, or too rare to capture on film. This is why new species are discovered on nearly every expedition. We're not even close to cataloging everything that lives down there, and we we may never be. The deep ocean is simply too large, too remote, and too difficult to access. Let me tell you about how life survives in a place with no sunlight. Because the food chain in the deep ocean is unlike anything on the surface. In the sunlight zone, photosynthesis is the foundation of life. Plants and phytoplankton convert sunlight into energy. Herbivores eat the plants. Carnivores eat the herbivores. Energy flows upward through the food chain. But in the Hadal Zone, there is no sunlight. There is no photosynthesis. So where does the energy come from? The answer is marine snow. Marine snow is the constant rain of organic particles falling from the upper ocean. Dead plankton, fecal pellets, bits of decomposing fish, fragments of larger animals, all of it slowly drifting downward through thousands of meters of water. By the time it reaches the Hadal Zone, most of the nutritious material has been consumed by organisms in the layers above. What's left is the scraps, the leftovers. But for creatures adapted to survive on almost nothing, it's enough. And occasionally, something extraordinary happens. A whale dies. Its massive body, weighing tens of tons, sinks to the seafloor. This is called a whale fall, and it's a bonanza for deep sea life. A single whale carcass can sustain an entire ecosystem for years, sometimes decades. First come the scavengers. Hagfish, sleeper sharks, amphipods, they strip the soft tissue, the blubber, the organs. Then come the opportunists. Crabs, worms, snails, they feed on the bones, which are rich in lipids. And finally, bacteria move in, breaking down what's left at the molecular level. A whale fall creates an oasis of life in the deep. Species that are normally rare become abundant. The seafloor around the carcass becomes a hub of activity, and when the whale is finally consumed, the ecosystem disperses, waiting for the next fall. But there's another source of energy in the deep, one that doesn't depend on anything falling from above. Hydrothermal vents. These are cracks in the seafloor where superheated water, reaching 400 degrees Celsius, pours out from deep within the Earth's crust. The water is rich in chemicals, hydrogen sulfide, methane, iron, manganese. And there are bacteria that can use these chemicals as an energy source. They don't need sunlight. They don't need photosynthesis. They perform chemosynthesis, converting chemical energy into biological energy. And these bacteria form the foundation of an entirely separate ecosystem. Around hydrothermal vents, you find tube worms over 2 meters long, giant clams, eyeless shrimp, all of them thriving in conditions that would kill most surface life. The water is near boiling. The chemicals are toxic. But life has found a way. Some scientists believe life on Earth may have begun in places like this, billions of years ago. Not in sunlit pools, but in the darkness, where chemicals, not light, fuel existence. But here's what most people don't understand about the Mariana Trench. It's not just a hole in the ocean floor. It's not a static feature. The Mariana Trench is an active system that's quietly reshaping Earth from below every single day. What happens there does not stay there. The Mariana Trench marks one of the most extreme boundaries on the planet. Here, the Pacific plate slowly bends and sinks beneath the smaller Philippine Sea plate. This motion is almost imperceptible on human timescales, measured in centimeters per year. Yet over millions of years, it becomes one of the most powerful forces shaping Earth. As the oceanic plate descends, it does not simply disappear. It carries with it enormous quantities of water locked inside minerals, along with carbon compounds and sediments that once settled on the ocean floor. These materials are dragged deep into the mantle, altering its chemistry and behavior. This process fuels volcanic arcs thousands of kilometers away and contributes to the constant recycling of Earth's crust. The Mariana Trench is not an isolated feature. It is part of a planetary system that regulates how the surface, the interior, and the atmosphere interact over geological time. In this sense, the trench acts as a gateway, a place where the surface world is slowly fed back into the planet's interior. At extreme depths, water behaves in unfamiliar ways. Under immense pressure, it penetrates minerals, alters crystal structures, and triggers chemical reactions that cannot occur at the surface. As the descending plate sinks deeper, water is released from the rocks and migrates upward into hotter regions of the mantle. This release lowers the melting point of surrounding material, making magma generation possible. Without this hidden transport of water, many of Earth's volcanoes would not exist. But water also plays another role. In the deepest parts of the trench, chemical gradients form between sediments, seawater, and rock. These gradients create sources of energy independent of sunlight. In such environments, life does not rely on photosynthesis. Instead, it draws energy from chemical reactions involving methane, hydrogen, and sulfur compounds. These processes resemble what scientists believe may have supported some of the earliest life on Earth. The Mariana Trench therefore offers a rare natural laboratory, a place where conditions echo those of a much younger planet. Despite its remoteness, the Mariana Trench is no longer untouched by human activity. Samples collected from the deepest sediments have revealed traces of industrial chemicals, microplastics, and persistent pollutants. These substances did not sink directly from the surface. They traveled slowly, attached to organic particles, descending over decades through the water column. Eventually, they reached a place once thought to be completely isolated from the modern world. The presence of these materials does not imply immediate ecological collapse. The deep-sea ecosystem is resilient in ways we do not yet fully understand, but it does serve as a record. The trench has become an archive of human activity, storing chemical signatures that may remain preserved for centuries. Even the most remote environments on Earth now carry evidence of global civilization. This realization shifts the meaning of depth. Distance alone is no longer a barrier. Let me be clear about what this means. We have polluted the deepest place on Earth, a place that took us until 1960 to even reach, a place where the pressure would crush a human instantly, a place more remote than the surface of Mars in terms of accessibility. And yet, our plastic is there, our chemicals are there, our fingerprint is there. This should concern you, not because the deep-sea ecosystem is about to collapse. It's survived for millions of years under conditions far more extreme than anything we can throw at it, but because it demonstrates that there is nowhere on Earth that is beyond our reach, nowhere that is safe from human impact. The creatures living in the Mariana Trench have evolved over millions of years to survive extreme pressure, near-freezing temperatures, and complete darkness. But they did not evolve to survive microplastics. They did not evolve to survive industrial chemicals. And we have no idea what the long-term effects of this pollution will be. As we close, I want to leave you with the questions that keep scientists awake at night. Because for all we've learned about the deepest darkness on Earth, there's so much more we don't know. How many species live in the Hadal Zone? We've documented about 400, but every expedition discovers new ones. The real number could be in the thousands or tens of thousands. We simply don't know. How do these organisms reproduce? We've observed adults, but we've rarely seen juveniles. Where do they spawn? How do they find mates in the darkness? How do their young survive the journey to adulthood? What is the full extent of chemosynthetic ecosystems? We've found hydrothermal vents and cold seeps, but are there other chemical energy sources we haven't discovered yet? Other ways for life to exist without sunlight. How connected are deep-sea ecosystems to surface processes? We know marine snow falls from above. We know whale falls provide nutrients. But are there other connections we're missing? Does what happens in the deep affect what happens at the surface? And perhaps most importantly, what happens if we lose these ecosystems? The deep ocean is being targeted for mining. Companies want to extract rare earth minerals from the seafloor, but we don't understand the ecosystems well enough to know what the consequences would be. If we destroy habitats that took millions of years to evolve, can they recover? Or will we lose species we never even knew existed? Exploring the Mariana Trench is not about chasing records or reaching extremes for their own sake. Each descent provides data that cannot be obtained anywhere else. Understanding how materials move from the surface into the mantle helps scientists model long-term climate stability. Studying organisms adapted to extreme pressure informs medicine, molecular biology, and material science. Observing how ecosystems function with minimal energy input challenges assumptions about the limits of life. The trench also reminds us that Earth remains an active, evolving planet. Vast processes unfold beneath our feet, independent of human timescales and concerns. We have mapped distant planets in greater detail than much of our own ocean floor. Yet here, beneath kilometers of water, lies a system that influences the planet's past, present, and future. The Mariana Trench is not simply the deepest place on Earth. It is a reminder that the most important processes often occur far from view. How much of Earth's inner workings still remain hidden beneath the oceans? What forms of life might exist beyond the limits we currently understand? And how will our growing presence shape even the most distant regions of the planet? The answers, for now, remain in the darkness below. But one thing is certain: what lives in Earth's deepest darkness is more extraordinary, more resilient, and more important than we ever imagined. And we've only just begun to understand it.